My name is Mildred. In this lesson, we will learn about distribution and frequency analysis in exploratory data analysis.
In the previous lesson, we learned about summary statistics. In this lesson, we will build on that to understand how values are distributed or categorized. The purpose of distribution and frequency analysis is to understand how values are distributed or categorized. It examines the shape of numerical distributions, category proportions, and skewness or imbalance. The methods it uses are histograms, density plots, frequency tables, and/or value counts. The questions it answers are: 1. Is the data normal, skewed, or uniform? 2. Which categories dominate? 3. Are classes balanced? In summary, distribution and frequency analysis help detect bias, imbalance, and unusual patterns.
Next, let's create a histogram of the examination score distribution.
On the screen, we see a snippet of the code we used to generate the data in the previous lesson, along with a histogram of exam score. The histogram is bell-shaped. A bell-shaped histogram indicates data that is symmetrically distributed, resembling a bell curve with a single high peak in the center. The highest frequency occurs at the mean, median, and mode, with data sloping downward evenly on both sides, commonly representing a normal distribution where most data falls near the center.
Let's talk a little bit about how to interpret histograms. If the histogram were right-skewed, it will mean it has high outliers. When a data set is right-skewed, the median is generally a better measure of central tendency than the mean because the mean is inflated by the extreme high-value outliers. If the histogram were left-skewed, it will mean low outliers. The mean is less than the median, which is also less than the mode, because the low values pull the average down. Again, the median is the best measure of central tendency for low-skewed or any skewed histograms, as it is resistant to extreme values and, unlike the mean, is not pulled toward the tail. It accurately represents the middle of the distribution, making it superior to the mean when data points are not symmetrically distributed.
Exam score distribution, range 37 to 100, mean 70, median 69.5, standard deviation 11.8, shape bell-shaped, meaning it is approximately normal.
Let's learn a bit about how to interpret the standard deviation. In our data, the mean examination score is 70 and the standard deviation is 11.8. This will be interpreted as most students scored between 58.2 and 81.8. This calculation is gotten by subtracting the standard deviation from the mean for the lower value and adding the standard deviation to the mean for the higher value. The value indicates a wider range of performance. We can approximate and say that most scores cluster between 60 and 80. Very few extremely low or extremely high values. No heavy skew detected. Interpretation. Exam scores are symmetrically distributed, indicating balanced performance across students. This suggests that the class does not show grade inflation. No extreme clustering at high or low performance. Exam score is suitable for modeling. Because the distribution is approximately normal, statistical tests assuming normality may be appropriate.
Distribution analysis. For our data set, we examine the age, study hours, attendance, and exam score.
Age distribution. Range 18 to 29. Mean 24. Median 24. Distribution approximately uniform since they are randomly generated integers. Interpretation of age distribution. Age is evenly spread across the college age range. No skew detected. No outliers present. Age is unlikely to dominate performance outcomes. In conclusion, the age variable is well-balanced and stable.
Study hours distribution. Mean 4.2 hours. Range 1 to 8 hours. Shape roughly normal. Distribution characteristics. Most students study between 3 and 5.5 hours. Few students study extremely low or high hours. Slight variation but no strong skew. Interpretation of the study hours distribution. Study hours appear normally distributed. This is ideal for correlation analysis and regression modeling because it avoids extreme skew. It allows linear modeling assumptions to hold better. This is a good example of a well-behaved continuous predictor variable. Attendance distribution. Range 60 to 100%. Mean 82%. Spread is wider than study hours. Slight clustering toward higher attendance. Distribution characteristics. Most students attend above 70%. Few students fall near the minimum threshold of 60%. Slight positive clustering at high values. Interpretation. Attendance shows variability but leans toward higher participation. This suggests that most students are engaged, and low attendance students may be a minority group worth analyzing. Possible segmentation. Low versus high attendance groups.
Frequency analysis, categorical variables. Now we analyze gender and major.
On the screen is the code snippet and the output of the value count of gender and major. From the output, we can see that male equals 50% and female equals 50%. This means that the dataset is balanced by gender. This is important because no sampling bias is present and group comparisons will be fair. Gender-based performance comparisons are statistically reliable.
Major frequency distribution. The majors we have in the dataset are CS, Math, and Business. The distribution is roughly evenly distributed across the three majors, with Business equals 68, CS equals 68, and Math equals 64. This means that no major dominates the dataset, and segment comparisons across majors are valid. No class imbalance concerns.
In summary, the overall distribution is as follows. Study hours has normal distribution. Exam score has approximately normal distribution. Attendance has slight clustering at high values. Age has uniform distribution. Gender distribution is balanced. Major is evenly distributed. The frequency and distribution analysis indicates that the student performance dataset is well-balanced and statistically stable. Numerical variables display approximately normal behavior, and categorical variables are evenly distributed. This suggests the dataset is clean, free from major bias, and appropriate for deeper relationship analysis and modeling.
In the next lesson, we will learn about correlation analysis. If you enjoyed this lesson, give us a like, leave a comment, turn on your notification, subscribe to the channel.
Hope Ikiyoekan is soon.